Gravity's ultimate victory lurks in the heart of almost every galaxy. These are not mere voids but supermassive black holes, cosmic giants whose secrets are only beginning to be uncovered. You are about to journey through 30 incredible facts that will completely reshape your understanding of these enigmatic powerhouses. By the end, you will grasp the true scale and influence of the universe's largest black holes. We will explore how a black hole can weigh as much as 66 billion suns and why our own galaxy's center is far from quiet. What single cosmic mystery do you find most compelling? Think of the black holes you often hear about, the ones formed when massive stars collapse. These stellar mass black holes are incredibly dense, but they are mere pebbles compared to the mountain ranges we are about to discuss. A supermassive black hole is a different class of cosmic monster entirely. Its mass is not measured in single suns, but in millions, even billions of them. Imagine squeezing our entire sun, with all its immense gravity and energy, into a sphere just a few miles across. Now multiply that by 10 million or by a billion. That incomprehensible concentration of mass is what we call a supermassive black hole, and they are not rare anomalies. These giants are thought to reside at the very heart of almost every large galaxy, including our own Milky Way, where a silent titan named Sagittarius, a star, holds sway. This is the scale we are dealing with, a scale so vast it redefines our understanding of power in the cosmos. For decades, black holes were cosmic phantoms, entities we knew existed but could never truly see. That all changed in April 2019, when a global team of scientists unveiled the impossible, a direct image of a black hole. This was not an artist's impression. It was a photograph of the supermassive giant known as M87 star, residing in a galaxy 55 million light-years away. The image, a fiery ring of light encircling a perfect circle of darkness, became an instant icon. That central shadow is the black hole's event horizon, the point of no return, silhouetted against the incandescent gas swirling around it. The bright ring itself is the photon ring, light itself bent into a perfect circle by the black hole's unimaginable gravity. Capturing this image was a feat of staggering proportions. It required the Event Horizon Telescope, which was not a single instrument but a planet-sized virtual observatory. 8 radio observatories across the globe, from the high deserts of Chile to the volcanoes of Hawaii, synchronized their observations to act as one gigantic telescope. The technical precision was like someone in New York reading the date on a quarter held in Los Angeles. This international collaboration, a testament to human curiosity, finally gave a face to one of the universe's most mysterious phenomena. Seeing that dark shadow confirmed a cornerstone of Einstein's theory of general relativity on a scale he could only have dreamed of. It proved that these gravitational titans are not just mathematical curiosities, but real, physical objects that shape the fabric of space itself. That iconic image of M87 star is a glimpse into the distant cosmos, but a similar giant lies right next door. At the very heart of our own Milky Way galaxy, a mere 27,000 light-years from Earth, resides Sagittarius, a star. This is the supermassive black hole that governs our galactic neighborhood. While it shares the same monstrous classification as M87 star, its behavior is strikingly different. Sagittarius, a star, is a quiet titan, a sleeping giant that currently emits very little radiation. Do not let its silence fool you, however. Its gravitational grip is absolute, holding an entire galaxy in its sway with a mass equivalent to 4 million of our suns. For years, its quiet nature made it difficult to study directly, but astronomers found a brilliant way to probe its secrets. They turned their telescopes not on the black hole itself, but on the stars dancing frantically around it. One star in particular, known as S2, has become a celestial laboratory. This massive hot star follows an extremely elliptical orbit that brings it breathtakingly close to the event horizon. At its closest approach, S2 hurtles around Sagittarius, a star at speeds exceeding 15 million miles per hour, a staggering 3% of the speed of light. It completes an orbit that takes our Sun 230 million years to complete around the galactic center in just 16 Earth years. This frantic dance is more than just a cosmic spectacle. By meticulously tracking S2's path for decades, scientists witnessed something extraordinary. The star's orbit does not trace a perfect static ellipse as Newtonian physics would predict. Instead, it precesses, meaning its point of closest approach shifts with every orbit. This rosette-shaped path is a direct and beautiful confirmation of the space-time curvature predicted by Einstein's theory of general relativity. We are living in an age where we can watch a star test the fundamental laws of physics in the violent grip of a supermassive black hole, all from our own galactic backyard. Yet even the immense power of our local giant pales before the true champions of the cosmos. Far beyond our galactic neighborhood, a colossus named Ton 618 reigns supreme. This is not merely a supermassive black hole, it is an ultramassive one, a cosmic behemoth of almost unimaginable proportions. Its mass is equivalent to 66 billion suns, a number so large it defies comprehension. To put that in perspective, our entire Milky Way galaxy, with its hundreds of billions of stars, has a total mass of only around 1.5 trillion suns. Ton 618 alone accounts for a significant fraction of that weight, but its true spectacle is not just its hidden mass, it is the brilliant beacon it creates. Ton 618 is a quasar, the hyperluminous heart of a distant galaxy. As unimaginable amounts of gas and dust spiral into its event horizon, they form a vast, searingly hot structure called an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with an intensity that outshines the combined light of every single star in its host galaxy. This single black hole system shines thousands of times brighter than our entire Milky Way, making it one of the most luminous objects in the entire known universe. It is a beacon from the early cosmos, its light traveling for over 10 billion years to reach us, offering a glimpse into an era when such monsters were more common. How does something so dark become the brightest light in the sky? The sheer scale of a 66 billion solar mass black hole forces a fundamental question. How does any object in the universe grow to such an immense size? The journey from a cosmic seed to a supermassive titan is a story written across billions of years, and astronomers have pieced together several compelling chapters. The most straightforward method is a process called accretion. Picture a vast whirlpool in space, but instead of water, it is made of gas and dust. As this material spirals inward toward the black hole, it does not fall straight in. It gathers in a furious, flat structure known as an accretion disk. Friction within this disk heats the gas to incredible temperatures, causing it to glow brilliantly before it finally crosses the event horizon, adding its mass to the black hole. It is a slow and steady feast that can last for eons, but accretion alone cannot explain the most colossal black holes we see in the early universe. They grew up too fast. This is where a more violent growth spurt comes into play. Galaxies frequently collide and merge throughout cosmic history. When two galaxies dance together, their central black holes are drawn toward the new galaxy's core. They begin a gravitational waltz of their own, eventually spiraling inward and merging into a single, more massive black hole. This cosmic cannibalism is a primary way for black holes to rapidly bulk up. Yet even this dramatic process has its limits. The existence of ultramassive black holes when the universe was still very young points to a third, more mysterious origin story. Some of the very first black holes may have been born big, not small. In the dense, primordial universe, giant clouds of pure gas could have collapsed under their own gravity. bypassing the star stage entirely and imploding directly into a black hole with a mass of tens of thousands of suns right from the start. These heavyweight seeds would have had a tremendous head start, allowing them to grow into the behemoths we observe today. The puzzle of their rapid growth remains one of the most active and fascinating areas of modern astrophysics, a mystery buried in the deepest reaches of time. That brilliant beacon of Ton 618 is a perfect example of a quasar, the most consistently luminous objects in the entire cosmos. A quasar is not the black hole itself, but rather the black hole's entire power system in a state of extreme activity. At its core is the supermassive black hole, but it is the frenzied process of accretion that creates the spectacle. When a black hole is surrounded by a vast reservoir of gas, dust, and even entire stars, that material does not simply vanish. It gets pulled into a flattened, spinning vortex called an accretion disk, whirling at velocities approaching the speed of light. The friction within this disk is so immense that it heats the material to millions of degrees, causing it to emit a blinding torrent of radiation across the entire electromagnetic spectrum, from radio waves to X-rays. This intensely bright region, the active galactic nucleus, is the quasar. Its luminosity is so staggering that it can outshine the collective light of every single star in its host galaxy, making the galaxy itself appear as little more than a faint smudge around a brilliant pinprick of light. This is how a gravitational trap, a region of darkness, becomes the brightest sustained source of light we can observe. Their sheer power makes quasars indispensable tools for astronomers. They act as cosmic lighthouses, their light piercing through billions of light-years of space. By analyzing this ancient light, we can study the composition of the intergalactic medium, map the large-scale structure of the universe, and peer back to an era just a few 100 million years after the Big Bang. These beacons from the dawn of time are ultimately powered by the most voracious black holes, monsters feeding at a rate that defies belief. The light of a quasar is not the only way a black hole proclaims its presence. These cosmic giants do not merely sit at the center of their galaxies as passive anchors. They actively shape the destiny of their stellar homes in a profound, symbiotic relationship. This connection is so fundamental that the mass of a galaxy's central bulge of stars is directly proportional to the mass of its supermassive black hole. It is as if the black hole and the galaxy grew up together, each regulating the other's growth. But how does a black hole, a sinkhole of gravity, influence an entire galaxy? The answer lies in a powerful process known as feedback. When a supermassive black hole actively feeds, it does not quietly consume its meal. The incredible energy released by the accretion process can be channeled into two colossal, opposing outflows. The first are searing winds of radiation and hot gas blasting outward from the accretion disk. The second, and even more dramatic, are jets. These are narrow, focused beams of superheated particles that shoot out from the black hole's poles at nearly the speed of light, stretching for hundreds of thousands of light-years into intergalactic space. These jets are cosmic blowtorches, and they carry enough energy to fundamentally alter the galaxy they call home. They plow into the vast clouds of cold gas that are the raw material for new stars. This does not gently push the gas aside. It violently heats it, scattering it, or blasts it entirely out of the galaxy. By doing so, the black hole effectively turns off the galactic star-forming factory. This might seem destructive, and on a local scale it is. But on a grand scale, this feedback is a crucial form of regulation. It prevents the galaxy from using all its gas too quickly in a burst of frantic star birth. It moderates the galaxy's growth, helping to determine its final size and structure, and can even determine whether a galaxy remains a vibrant spiral or settles into a quiet, elliptical retirement. The greatest mystery of all is that this feedback might ultimately spell the black hole's own doom. By quenching star formation and clearing away its own food supply, the black hole may eventually starve itself into a state of quiescence, like our own Sagittarius, a star. In this way, the most powerful force in the galaxy may also be the architect of its own silence. That point of no return, the black hole's ultimate boundary, has a precise mathematical definition known as the Schwarzschild radius. It is the distance from the center of a black hole at which the escape velocity becomes equal to the speed of light. Since nothing in the universe can travel faster than light, crossing this invisible threshold is a one-way trip. A helpful, though simplified, way to picture this is to think about launching a rocket from a planet. A small planet has weak gravity, so a rocket does not need much speed to escape. But if you could crush that planet into a smaller, denser sphere, its gravity at the surface would intensify. Crush it enough, and the escape velocity would eventually reach the speed of light. The sphere defined by that critical size is the Schwarzschild radius, and the surface of that sphere is the event horizon. For our own Sun, if you could compress all of its mass into a perfectly dark sphere, that sphere would be just under 2 miles across. That is the Sun's personal Schwarzschild radius, a tiny shadow of its current brilliant self. But for the supermassive giants we have been discussing, this boundary is not tiny at all. The event horizon of M87 star, the first black hole we ever imaged, is not a mere few miles across. Its Schwarzschild radius defines a sphere so vast it could comfortably contain our entire solar system out beyond the orbit of Neptune. The diameter of its event horizon is calculated to be about 24 billion miles. Now consider the true Leviathan, Ton 618. With a mass of 66 billion suns, its event horizon is almost incomprehensibly large. The Schwarzschild radius for this ultramassive black hole stretches over 390 billion miles. This means the boundary of this single black hole, the point where light itself gives up, is wider than our entire solar system by a factor of thousands. If you were to place Ton 618 where our Sun is, its event horizon would extend well beyond the Oort cloud, the distant shell of icy bodies that marks the solar system's frontier. This is not a pinprick of darkness, it is a yawning chasm of nothingness on a truly stellar scale. A perfect sphere of ultimate gravity so large it could swallow countless stars and planets without a trace. This gravitational grip is so powerful it can twist the fabric of the universe into a lens. A supermassive black hole does not just trap light that ventures too close, it bends the very path of light passing at a safe distance, a phenomenon known as gravitational lensing. According to Einstein's theory, a massive object warps the space-time around it, creating a kind of gravitational well. Light, traveling in a straight line through this curved space, appears to bend from our perspective. A black hole creates the deepest possible well, and the lensing effect is spectacular. It can magnify, distort, and even multiply the light from a distant galaxy located directly behind it from our point of view. The most perfect manifestation of this is an Einstein ring, a near-complete circle of light encircling the black hole. This beautiful halo is not real, it is an illusion of geometry. The black hole's gravity has smeared and stretched the single, true image of the background galaxy into a perfect ring. If the alignment is slightly off, you might see not a ring, but multiple mirrored images of the same cosmic object arrayed around the central darkness. This is more than just a cosmic curiosity, it is one of astronomy's most crucial tools. By measuring the degree of this bending, how much the light is distorted, and how large the Einstein ring appears, scientists can perform a direct weigh-in. They can calculate the mass of the invisible black hole causing the distortion, essentially using the bent light as a cosmic scale. This allows us to measure the mass of objects we can never see directly, confirming the staggering weight of these dark giants by watching how they contort the very light of the universe. This warping of space does something even more profound to time itself. If you could somehow hover just outside the event horizon of a supermassive black hole, you would experience one of the universe's strangest truths. Time, which feels so constant to us, is not absolute. It is stretched and twisted by gravity, a phenomenon called time dilation. Imagine a pair of astronauts on a daring mission. One, the explorer, descends toward the black hole's event horizon in a sturdy ship. The other, the observer, remains in a safe, distant orbit. As the explorer gets closer to that point of no return, a bizarre disconnect unfolds. For the explorer, time feels normal. Their watch ticks second by second, their heart beats at its usual rhythm. But for the observer watching through a powerful telescope, the descent appears to happen in extreme slow motion. The explorer's movements would become glacial, their ship's signals stretched into lower and lower frequencies until they seem to freeze completely, hovering forever at the brink of the event horizon without ever quite crossing it from the observer's perspective. This is not an illusion or a trick of the light. It is a direct consequence of the black hole's gravity, dramatically slowing the passage of time itself in that region. The closer you get to the immense gravitational well, the more time slows down relative to the wider universe. While mere hours might pass for the brave explorer near the horizon, thousands or even millions of years could rush by for the observer and the galaxy they left behind. You would return to a future so distant your own civilization might be long forgotten. This is not science fiction, but a verified prediction of Einstein's general relativity, and we account for its tiny effects every day with the GPS satellites orbiting our own planet. Near a black hole, however, this gentle curve becomes a cosmic cliff face. The universe seems to protect its deepest secrets by making time itself stand still for anyone who dares to approach them. The very fabric of space itself, it turns out, is not entirely empty. This quantum whisper holds the key to the most surprising fact of all, that black holes are not completely black. Stephen Hawking made the startling prediction that black holes can, in fact, evaporate. His theory merges the vast scale of general relativity with the bizarre, probabilistic world of quantum mechanics. It proposes that at the very edge of the event horizon, pairs of virtual particles constantly flicker in and out of existence. Normally, these particle pairs annihilate each other almost instantly. But if one particle falls into the black hole, its partner is left stranded, escaping into space as real radiation. This stolen energy comes at a direct cost to the black hole's mass. Over unimaginable eons, this slow leak, known as Hawking radiation, would cause the black hole to gradually shrink and ultimately vanish. Yet for the supermassive giants we have been discussing, this theoretical evaporation is less a death sentence and more a slow sigh. The rate of Hawking radiation is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it glows with this radiation and the faster it evaporates. A black hole with the mass of a small asteroid would shine with the heat of a blast furnace and vanish in a fraction of a second. But a supermassive black hole is so cold from a Hawking radiation perspective that it is practically frozen in time. A black hole like Sagittarius, a star with its 4 million solar masses, would take an almost inconceivable 10 to the 87th years to evaporate. That is a 1 followed by 87 zeros. The current age of our universe is only 13.8 billion years, a number with a paltry 10 digits. This means a supermassive black hole's lifespan is longer than all the stars that will ever shine. They are not decaying away, they are the most permanent structures in the cosmos, destined to outlast every galaxy, every star, and every proton. Hawking's radiation theory introduces a profound cosmic puzzle, one that strikes at the very heart of our understanding of reality. This is the black hole information paradox. According to the fundamental rules of quantum mechanics, information about the universe can never be truly destroyed. It can be scrambled, transformed, or hidden, but it must always, in principle, be recoverable. A book burned to ashes still contains the same information in the arrangement of its atoms, however difficult it might be to read, but a black hole presents a terrifying exception. Imagine throwing that same book into a supermassive black hole. According to general relativity, the book is lost forever, its information trapped behind an event horizon from which nothing returns. Later, as Hawking radiation slowly causes the black hole to evaporate, that radiation is purely thermal. It is random, featureless heat carrying no details whatsoever about the book's title, its author, or the words printed on its pages. The information is seemingly erased from the universe, violating a core principle of quantum physics. This creates a direct conflict between our two most successful theories of nature. Either general relativity is wrong about the fate of what falls in, or quantum mechanics is wrong about the permanence of information. Supermassive black holes make this paradox even more profound because of their sheer longevity. The slow trickle of their Hawking radiation means the information swallowed over billions of years would be locked away for trillions upon trillions more, stretching the paradox across a timeline that dwarfs the age of the cosmos itself. Do the stories of every star and planet ever consumed simply vanish into the void? Or is our picture of the event horizon fundamentally incomplete? Resolving this paradox might require a revolution in physics, forcing us to see space and time in a completely new way. The universe holds black holes so large their masses border on the abstract. While Ton 618 reigns as the champion we have already met, with its 66 billion solar masses, it is not alone in this ultramassive class. Consider the Phoenix Cluster's central black hole, often called Phoenix A. Nestled within one of the most massive galaxy clusters known, this colossal entity is estimated to weigh in at a staggering 100 billion times the mass of our Sun. Its appetite is fueled by the vast reservoir of hot gas that permeates its cluster, a seemingly endless feast that allows it to maintain its incredible size. Then there is SDSSJ 14082 plus 025733.2, a quasar whose name is a catalog number but whose nature is spectacular. This distant beacon, shining from over 12 billion light-years away, harbors a black hole measured at 12 billion solar masses. The very existence of such a giant when the universe was less than a billion years old presents a monumental challenge to our theories of cosmic growth. How do we even weigh such impossibly distant objects? For quasars like these, astronomers often use a technique called reverberation mapping. They observe the brilliant, flickering light of the accretion disk. By carefully measuring the time delay between changes in the light from the hot gas close to the black hole and the response from cooler gas further out, they can effectively map the structure of this inner region and calculate the gravitational force and thus the mass of the central engine. It is a cosmic echolocation, using light itself to probe the darkness. Each of these record holders, from the nearby to the ancient, pushes the boundaries of what we thought was possible, forcing us to reconsider how the cosmos builds its most immense structures. The true weight of these cosmic giants is not measured on any physical scale, but through brilliant celestial detective work. Astronomers have developed several ingenious methods to perform a cosmic weigh-in, using the fundamental laws of physics as their ultimate guide. The most intuitive technique, and one used for our own galactic center, is stellar dynamics. By meticulously tracking the orbits of stars whirling around a black hole, scientists can directly apply Newton's laws of motion, refined by Einstein's relativity. The speed of a star's orbit reveals the gravitational pull it is experiencing. A star whipping around a distant point at 15 million miles per hour tells you the immense mass required to hold it in that path. It is like watching a handful of marbles spin around a central drain, their velocities painting a perfect picture of the unseen force binding them. For closer, quieter black holes like Sagittarius, a star, this method is incredibly precise, giving us a reliable mass measurement of 4 million suns. When a black hole is more distant or shrouded in dust, a different tracer is needed. In these cases, astronomers turn to the motion of glowing gas clouds. These vast clouds orbit the central black hole, and their light reveals their speed through the Doppler effect. The same principle that makes a siren's pitch change as it races past you applies to starlight. Gas moving toward us has its light shifted to the blue end of the spectrum, while gas moving away is shifted to red. By mapping this red and blue shifting across the galaxy's core, astronomers can chart the velocity of these clouds and calculate the mass of the invisible anchor they are circling. But sometimes nature provides an even more precise tool, a natural laser known as a water maser. In the dense, warm accretion disks of some active black holes, water molecules can be excited to emit a very specific, narrow radio signal. These maser spots act like a series of brilliant, stationary beacons. By tracking their motion with ultra-high-resolution radio telescopes, scientists can map the rotation of the disk with phenomenal accuracy, effectively placing the black hole on a scale of exquisite precision. For the most luminous and active supermassive black holes, the quasars, a third powerful method comes into play: reverberation mapping. This technique relies on the brilliant, flickering light of the accretion disk itself. Imagine the chaotic environment around the black hole. Close in, hot gas whips around at incredible speeds, emitting broad emission lines in its spectrum. Further out, cooler gas moves more slowly, emitting narrower lines. When the intense light from the inner disk flares up, it illuminates this outer gas after a short time delay. By carefully measuring the time lag between a flare in the continuum light and the corresponding response in the broad emission lines, astronomers can determine the distance from the black hole to that surrounding gas cloud. Since the width of the emission line reveals the velocity of the gas, combining velocity with distance allows for a direct calculation of the central mass. It is a form of cosmic echolocation, using the delay of light echoes to map the gravitational heart of a quasar billions of light years away. Each of these methods, from watching stellar dances to catching light echoes, confirms the same staggering reality that darkness can be weighed by the light it commands. The existence of these cosmic giants so soon after the dawn of time presents a monumental puzzle. How could supermassive black holes with masses of billions of suns appear when the universe was less than 1 billion years old? For them to grow so immense so quickly, they needed a tremendous head start, and astrophysicists are racing to uncover the nature of that initial seed. One compelling theory points to the very first generation of stars. These population 3 stars were not like the stars we see today. They were behemoths composed purely of hydrogen and helium, and they could form with masses hundreds of times that of our Sun. Such colossal stars would have lived fast and died young, burning through their nuclear fuel in only a few million years before collapsing directly into black holes with masses of perhaps a few hundred suns. These stellar mass black holes would have been the seeds scattered across the young cosmos, ready to begin their long feast. Yet even these massive seeds might not be enough to explain the most ancient quasars we observe. Their growth would have had to be unnervingly efficient, pushing the limits of what we believe is physically possible. This has led to an even more dramatic hypothesis, the direct collapse model. In the dense, pristine gas of the early universe, vast clouds could have collapsed under their own gravity without ever fragmenting into stars. This monolithic collapse would have created a supermassive black hole seed in one single, spectacular event. A seed weighing not hundreds, but tens of thousands or even 100,000 solar masses right from its birth. This cosmic shortcut would provide the perfect foundation for building a billion solar mass monster within the universe's first billion years. A third, more speculative idea involves the universe's most mysterious component, dark matter. Could certain types of dark matter particles have clumped together in the early universe, creating ultra-dense cores whose gravity pulled in normal matter, leading to a rapid and direct collapse into a massive black hole? This remains a frontier of theoretical physics, but it highlights the depth of the mystery. The truth is, we may need a combination of all these processes. Some early black holes may have grown from stellar seeds, while others were born as titans through direct collapse. Finding the very first quasars with the next generation of telescopes, like the James Webb Space Telescope, is our best chance to peer back into this formative era and finally read the first chapter in the life story of these dark giants. Our search for the origins of cosmic giants leads us to a ghost in the graveyard, a class of black holes that has proven incredibly elusive. These are the intermediate mass black holes, the missing link in our cosmic family tree. They are thought to bridge the gap between the small, stellar mass black holes and the supermassive ones that rule galaxies, with masses ranging from a few hundred to a few 100,000 times that of our Sun. Finding them would be like discovering the fossilized adolescent of a long-extinct titan, a crucial piece of evidence showing how supermassive black holes grew from humble seeds into the monsters we observe. For decades, they were purely theoretical, but recent observations have begun to shed light on these shadowy objects. Some of the strongest candidates have been found not in the bright hearts of galaxies, but in the sparse outskirts of globular clusters. These dense, ancient swarms of stars are cosmic retirement communities, and they may harbor a dark secret at their core. The motion of stars in clusters like Omega Centauri suggests they are whirling around a central, invisible mass of tens of thousands of suns. Another compelling candidate emerged from the detection of a gravitational wave signal known as GW190521. This ripple in spacetime was created by the merger of two black holes, and the resulting single black hole weighed in at a stunning 142 solar masses, placing it squarely in the intermediate mass range for the first time. This was a direct confirmation that such objects do indeed exist. Why are they so hard to find? Their nature makes them stealthy. A stellar mass black hole reveals itself by violently stripping material from a companion star, creating bright X-rays. A supermassive black hole announces its presence with a brilliant quasar or by orchestrating the dance of millions of stars. But an intermediate mass black hole, especially one floating alone in intergalactic space, has a much weaker gravitational pull. It may only occasionally snack on a passing star, producing a faint and fleeting flare that is easy to miss. Their quiet nature makes them the universe's best hide-and-seek players. Uncovering more of them is one of astronomy's great quests, because each one is a potential blueprint, a preserved seed that holds the untold story of how our universe builds its greatest gravitational marvels. These black holes are not just passive consumers, they are cosmic power plants capable of launching the most energetic eruptions in the universe. When conditions are right, a feeding supermassive black hole can fire two narrow, opposing beams of superheated plasma directly from its poles. These are relativistic jets, and they are the universe's ultimate particle accelerators. The material in these jets does not just drift out, it is violently ejected at velocities so close to the speed of light that the effects of Einstein's special relativity become starkly apparent. Their power source is a breathtaking combination of the black hole's immense gravity and its rapid spin. As the black hole rotates, it drags the very fabric of space-time around with it, an effect known as frame dragging. This spinning motion, combined with intensely wound-up magnetic fields anchored in the accretion disk, acts like a colossal slingshot. Some of the infalling material, instead of crossing the event horizon, gets channeled along these magnetic field lines and hurled outward from the polar regions. The result is a tightly focused beam of energy that can punch through the surrounding galaxy and extend for millions of light years into intergalactic space. We can see the effects of these jets across the entire electromagnetic spectrum. They glow in radio waves, creating vast lobes that often dwarf the galaxy that spawned them. They emit X-rays as they slam into the tenuous gas that exists between galaxies, and they can even produce the highest energy gamma rays ever detected. In some extreme cases, these jets are pointed almost directly at Earth, a configuration that makes them appear incredibly bright and variable, earning them the name blazars. The impact of these outflows is profound. They inject enormous energy into the cosmic voids, heating the intergalactic medium and preventing it from cooling and collapsing to form new galaxies. They are the black hole's long-reaching arm, capable of shaping not just its own galaxy, but the entire cosmic web around it. Despite their terrifying complexity, black holes are surprisingly simple at their core. This profound idea is captured by the no-hair theorem, a concept that suggests these cosmic monsters are, in a fundamental way, bald. They possess no distinguishing features, no unique hairstyles. According to this theorem, a black hole can be completely described by only three simple properties: its mass, its electric charge, and its spin. Everything else, every single detail about whatever fell in, is irretrievably lost. Imagine throwing a grand piano, a library of encyclopedias, and a mountain of confetti into a black hole. From the outside, you would never know what was inside. The black hole would not be made of piano-shaped or confetti-colored material. It would simply gain a little more mass, its spin might change slightly, and its overall electric charge could shift by a tiny amount. The intricate information about the objects, the piano's wood grain, the words in the books, the colors of the confetti, is completely erased. This radical simplicity emerges from the very nature of the event horizon, that one-way membrane that shreds away all complexity. It does not matter if the black hole formed from a collapsing star made of pure hydrogen or from the remnants of 1,000 different planets. Once the dust settles and the black hole reaches a stable state, it becomes a perfect, featureless entity defined only by those three numbers. This is both a relief and a profound puzzle for physicists. It is a relief because it means that the impossibly complex physics of gravity and quantum fields inside a black hole have a very simple representation on the outside. We do not need to know the fate of every single atom to understand the black hole's gravitational field, but it is a profound puzzle because this simplicity directly fuels the black hole information paradox. If a black hole can be described with just three parameters, then what happens to all the other information that define the objects that fell in? The no-hair theorem paints a picture of ultimate entropy, a state of maximum disorder where all distinguishing features are smoothed away into a perfect dark sphere. It tells us that the universe may have a fundamental eraser, and that the deepest secrets are not just hidden, but perhaps permanently forgotten. That radical simplicity hides a gravitational reality so extreme it can stretch you into a strand of cosmic pasta. This process has a fittingly bizarre name: spaghettification. It is the ultimate tug of war, a battle between the pull of gravity on your feet and the pull on your head. If you were falling feet first toward a stellar mass black hole, the gravitational pull at your feet would be vastly stronger than the pull at your head just a few feet away. This difference in force, the tidal force, would stretch you lengthwise like a piece of taffy. Simultaneously, the sides of your body would be compressed inward by the same forces, squeezing you from all directions. The result would be as gruesome as it is inevitable. You would be transformed into a long, thin stream of atoms before you even reached the event horizon. But here is the astonishing twist. This fate is not guaranteed for every black hole encounter. The intensity of these tidal forces does not just depend on the black hole's mass, it depends on how compact that mass is. For a small black hole, the event horizon is very close to the central point of infinite density, creating an incredibly steep gravitational gradient. It is like standing on a needle, a sharp, sudden cliff of gravity. For a supermassive black hole, however, the story is completely different. Its event horizon is not a tiny point, it is a vast sphere. The distance from the central singularity to the event horizon is enormous. This means the gravitational gradient at the event horizon itself is much more gentle. The difference in pull between your head and your feet would be far less severe. If you were falling toward a supermassive black hole like Ton 618, you could theoretically cross the event horizon intact before the tidal forces had a chance to pull you apart. You would not feel a sudden rip or a violent jerk at the boundary. You would simply and silently pass the point of no return. Of course, your journey would not end there. As you continued to fall inward, the tidal forces would gradually intensify. Eventually, far beyond the horizon, the stretching would begin. But for a brief, surreal moment, you could cross the ultimate threshold and peer into the abyss, a final tourist in a place from which no postcard can ever be sent. The silent dance of merging black holes sends tremors through the cosmos itself. In September 2015, humanity felt one of these tremors for the very first time. The LIGO and Virgo observatories detected a ripple in space-time, a gravitational wave generated over 1 billion years ago by two stellar mass black holes spiraling into each other. This was not a flash of light or a burst of radiation. It was a direct vibration in the fabric of reality, confirming a key prediction of Einstein's theory. The event was cataclysmic. For a fleeting moment, the merging black holes radiated more power than all the stars in the observable universe combined. Yet these were the small players. The true cosmic crescendo awaits us. Imagine the collision not of two stellar mass black holes, but of two supermassive giants, each weighing billions of suns. Their merger would not create a brief chirp, but a deep, resonant thunderclap in spacetime, a wave that could last for years. Our current ground-based detectors are deaf to this low-frequency song, but a future space-based observatory called LISA is being designed to listen. The Laser Interferometer Space Antenna would consist of 3 spacecraft flying in a perfect triangle millions of miles apart, connected by lasers. This colossal instrument would float in the quiet of space, far from Earth's seismic noise, allowing it to sense the long wavelength gravitational waves from the most massive collisions in the universe. What would it hear? The final waltz of 2 supermassive black holes, a slow, building hum as they circle each other for millennia before a final, universe-shaking merger. The energy released would dwarf anything we have ever observed, distorting the space between galaxies and offering a pure, unadulterated view of gravity in its most extreme form. This is the next frontier, where we move from feeling the small ripples to hearing the deep, fundamental bass notes of the cosmos. The shadow of a supermassive black hole is immense, but it is dwarfed by a far greater and more mysterious presence, dark matter. This invisible substance, which makes up over 85% of the matter in the universe, forms vast spherical halos that envelop entire galaxies. We cannot see it, but we feel its gravitational pull on the stars swirling at the edges of galaxies. Could there be a hidden conversation between this dark halo and the dark giant at the galaxy's core? One compelling theory suggests that dark matter acts as a cosmic architect, indirectly guiding the growth of the central black hole. The immense gravity of the dark matter halo dictates how a galaxy forms and evolves, funneling vast streams of gas toward the center. This steady supply of fuel feeds the supermassive black hole, allowing it to grow to a mass that is mysteriously proportional to the galaxy's central bulge of stars. The dark matter provides the structure, and the black hole grows to match that structure's scale. But what if the connection is even more direct? Some of the most exotic theories in physics propose that dark matter itself could collapse to form black holes. We usually think of dark matter as a sea of ghostly, non-interacting particles. However, certain hypothetical models suggest a different kind of dark matter, one that can interact with itself and clump together under its own gravity. In the ultra-dense environment of the early universe, these self-interacting dark matter particles could have collapsed directly into black holes, bypassing the need for stars entirely. These primordial black holes, born from the darkness itself, could have been the initial seeds for the supermassive giants we see today. They would have been woven into the fabric of the cosmos from its very first moments, providing the head start needed to explain the ancient quasars we observe. This idea remains highly speculative, a frontier where cosmology meets gravity in its most extreme form. Yet it highlights a profound possibility that the two greatest mysteries of the cosmos, dark matter and supermassive black holes, might not just be neighbors but family. The light from a feeding black hole is never steady. It flickers, flares, and fades in a chaotic cosmic dance. This variability is a hallmark of active galactic nuclei, and it tells a story of the violent environment just outside the event horizon. The brilliant glow of a quasar does not come from a single, stable light bulb, but from a churning, turbulent maelstrom of superheated gas. As vast clouds of material spiral inward, they do not move in a smooth, orderly flow. They clump and collide, creating pockets of intense friction and heating that burst into sudden, unpredictable flares of brightness. These are not gentle changes. A quasar can double its luminosity in a matter of hours, a flicker so rapid it places a strict limit on the size of the region responsible. The principle is simple: an object cannot change its overall brightness faster than light can travel across it. If you see a flare that lasts only 1 hour, the engine driving that flare cannot be much larger than the distance light travels in 1 hour, which is about 1 billion kilometers. That might sound vast, but for a black hole that can swallow solar systems, it is an incredibly compact volume. This rapid flickering forces the brilliant core of the accretion disk to be astonishingly small, a tiny, frantic powerhouse buried deep within the gravitational well. Astronomers use these flickers like a doctor uses a stethoscope, listening to the heartbeat of the black hole to diagnose its inner structure. By meticulously tracking how the light changes across different colors, from X-rays to visible light, they can perform a technique called reverberation mapping. A flare in the hot, inner disk will later illuminate cooler gas clouds further out, causing their specific light signatures to brighten after a short delay. By measuring this time lag, scientists can literally map the distances between the black hole, the accretion disk, and the surrounding clouds of gas. Each flicker is a cosmic echo, painting a picture of the invisible architecture around the ultimate darkness. Our galaxy's quiet heart holds echoes of a violent past. Stretching 25,000 light-years above and below the galactic plane, two colossal orbs of gamma-ray energy loom known as the Fermi bubbles. These are not gentle clouds, they are the faint, lingering remnants of a titanic explosion, a ghostly signature etched into space. Their existence points to an astonishing truth: our own Sagittarius, a star, was not always the sleeping giant we observe today. Millions of years ago, it must have awakened in a cataclysmic outburst of power. This was not a quiet meal, but a ferocious feast where the black hole consumed a vast amount of material, perhaps an entire star cluster or a massive gas cloud. As this matter spiraled into the abyss, the immense energy released did not just create a brilliant quasar like those in distant galaxies. A significant portion of that power was funneled into two opposing jets, erupting from the black hole's poles and blasting directly out of the galaxy. These jets, moving at a fraction of the speed of light, plowed through the galactic halo, shocking and heating the thin gas that resides there. The Fermi bubbles are the still glowing aftermath of that ancient collision, the searing hot edges of a cavity carved out by that long-ended eruption. We are living in the quiet aftermath of a galactic-scale event, looking up at the fading scars from a time when our own backyard was as violent and luminous as any quasar in the deep cosmos. The most radical theories in cosmology suggest our universe may be just one page in an infinite cosmic library. This is the multiverse hypothesis, and supermassive black holes could be its gatekeepers. Within the enigmatic singularity at a black hole's heart, our known laws of physics break down completely. General relativity predicts a point of infinite density, but many physicists suspect this is a sign that our current understanding is incomplete. Some speculative models propose that instead of a dead-end singularity, the core of a supermassive black hole could undergo a cosmic bounce. In this scenario, the extreme collapse of matter does not end in a point of nothingness but rebounds, triggering a new Big Bang in a separate, disconnected spacetime. Our entire universe, with its hundreds of billions of galaxies, could itself be the interior of a black hole existing within a parent cosmos. This idea, known as cosmological natural selection, paints a picture where black holes are birthing chambers for new universes. Each new universe could have slightly different fundamental constants and physical laws. In this vast cosmic genealogy, our universe's ability to produce so many stars and black holes makes it a fertile parent, spawning countless offspring realities. The supermassive black holes we observe would then be more than just gravitational traps. They would be potential portals, one-way doors to entirely new cosmic lineages. While this remains a highly theoretical and unproven concept, it transforms these dark giants from ultimate endpoints into possible beginnings, suggesting that the end of one story might just be the first chapter of another. This radical idea challenges our most basic intuition about reality itself. The holographic principle suggests that our perception of a three-dimensional world might be a magnificent illusion, a projection from a two-dimensional surface. Think of the security hologram on your credit card. It appears to have depth and volume, but all of its information is actually encoded on a flat, two-dimensional piece of plastic. The holographic principle proposes that our universe, in all its vast three-dimensional glory, might operate in a similar way. The information describing everything within a volume of space, every star, every planet, and every person, could be entirely encoded on its two-dimensional boundary. This is not just a philosophical curiosity. It emerged directly from the study of black holes and their baffling information paradox. A black hole's entropy, which is a measure of its hidden information, was found to be proportional not to its volume, but to the surface area of its event horizon. The amount of information a black hole can contain is limited by the size of its spherical surface, not by the space within it. This was the first hint that the universe might be storing its data on cosmic walls, not in cosmic rooms. Supermassive black holes, with their immense event horizons, become the ultimate testing grounds for this theory. Their vast, dark surfaces could be the universe's highest capacity hard drives, with every bit of information about what fell in somehow preserved or projected onto that two-dimensional shell. If this is true, then the three-dimensional reality we experience, from the flight of a bird to the spin of a galaxy, is a holographic projection of data written on the distant boundary of the cosmos. The event horizon of a supermassive black hole is not just a point of no return, it is a cosmic screen, and we may all be part of the show. To truly see the fury of a feeding black hole, you must look with X-ray eyes. Much of the violent drama surrounding these giants unfolds in the high-energy part of the spectrum, invisible to our ordinary telescopes. For over 2 decades, the Chandra X-ray Observatory has been our window into this searing realm, a spacecraft specifically designed to detect the faint whispers of X-rays coming from the deepest voids. Where optical telescopes see only obscuring clouds of dust, Chandra's vision cuts straight through, revealing the heart of the storm. Its primary target is the accretion disk itself, where gas is heated to millions of degrees by immense friction and gravitational forces. This superheated plasma glows not in visible light but in powerful X-rays, and Chandra maps this brilliant, tortured maelstrom with stunning precision. It allows scientists to measure the temperature, density, and rotation of the disk mere light hours from the event horizon, tracing the final, frantic orbits of matter before it vanishes forever. But Chandra's view extends far beyond the disk. It also captures the staggering power of the relativistic jets. As these beams of particles slam into the tenuous gas of intergalactic space, they create colossal shock waves that glow brilliantly in X-rays. Chandra has imaged these jets stretching for hundreds of thousands of light years, their energetic footprints revealing the incredible efficiency of the black hole's cosmic engine. Without this unique perspective, we would be blind to the most energetic processes in the universe, missing the true scale of a black hole's influence. Chandra transforms these dark giants from abstract ideas into dynamic, violent, and measurable forces, showing us a universe where the most illuminating discoveries are written in invisible light. That single, static image of M87 star was a monumental first step, but it was only a single frame in a cosmic motion picture. The next great leap in black hole science is to make that picture move. The global collaboration behind the Event Horizon Telescope is already pushing toward this goal, with ambitious plans to add new radio dishes to its planet-spanning array. By placing telescopes in new locations, particularly across Africa and in Antarctica, the virtual telescope's resolution will sharpen dramatically. It would be like adding more pixels to a camera, revealing finer details in the fiery ring of light and the dark shadow within. But the ultimate vision reaches beyond our atmosphere. Scientists are designing concepts for a space-based radio observatory, a fleet of satellites orbiting Earth and acting as a single immense eye. Freed from the blurring effects of our atmosphere and the physical limits of Earth's size, this space array could achieve a resolution hundreds of times greater than anything possible on the ground. What could we see with such a powerful instrument? We could watch the accretion disk itself in motion. Instead of a blurry, static donut of light, we would witness individual clumps of superheated gas whipping around the event horizon at near light speed. We could track their orbits over hours, days, and weeks, creating the first ever movie of a black hole's dynamic environment. This is not just about a prettier picture. A moving image would be a direct test of general relativity in its most extreme regime. Does the accretion disk behave exactly as Einstein's equations predict? Does the black hole's immense spin, dragging spacetime around with it, warp the disk's shape in the way we expect? By watching the flow of matter in real time, we could measure the black hole's spin with unprecedented accuracy and potentially spot deviations that point toward new physics. We would no longer be studying a portrait, but observing a living, breathing system, a gravitational giant whose every move tells a story about the fundamental nature of our universe. This conversion of matter into pure energy is perhaps the most efficient process in the entire cosmos. A supermassive black hole operating as a cosmic engine can achieve an efficiency far beyond anything we can replicate. While our most advanced nuclear reactors convert less than 1% of matter into energy, a spinning black hole's accretion disk can achieve an efficiency of up to 40%. This means that nearly half the mass of the material falling in is transformed into radiation and kinetic energy before it ever crosses the event horizon. That raw power is then channeled into two primary outputs that echo across the universe. The first is the brilliant radiation we see across the electromagnetic spectrum, from the blinding light of quasars to the penetrating X-rays mapped by observatories like Chandra. This radiation alone can outshine every star in a galaxy combined, flooding interstellar space with so much energy that it can strip galaxies of their star-forming gas. The second, more direct output is kinetic energy, the sheer physical motion of matter. This is the power behind the colossal winds and jets that blast outward from the galactic core. These are not gentle breezes, they are galaxy-scale hurricanes of charged particles, moving at a significant fraction of the speed of light and carrying enough force to blow the raw material for new stars clear out of the galaxy. This is the engine's feedback mechanism in its most potent form, a self-regulating system where the black hole's own growth eventually shuts down the very process that feeds it. But the influence of these engines does not stop at the galactic borders. When a quasar's jet plows into the thin plasma that exists between galaxies, it creates massive bubbles and shock waves that ripple through the cosmic web. These events heat the intergalactic medium, preventing it from cooling and collapsing to form new dwarf galaxies that would otherwise orbit the larger one. By doing so, supermassive black holes directly influence the population and distribution of galaxies across billions of light years. They are not mere inhabitants of the cosmic architecture, they are its active engineers, using unimaginable gravitational power to sculpt the largest structures in existence. These silent giants hold the universe's oldest memories. The faint glow from a distant quasar is more than just ancient light. It is a fossilized whisper from a time when the cosmos was young and raw. When we observe a quasar like TUN 618, its light has been traveling for over 10 billion years to reach us. We are not seeing it as it is today, but as it was when the universe was only a quarter of its current age. The light from even more distant quasars allows us to peer back to the end of the cosmic dark ages, that mysterious era before the first stars and galaxies fully illuminated the cosmos. This light acts as a probe, passing through vast clouds of primordial gas on its long journey to Earth. As it does, the gas imprints a unique chemical signature onto the light, like a cosmic barcode. By carefully decoding this barcode, astronomers can determine the composition of the universe mere hundreds of millions of years after the Big Bang. They can measure the ratios of the simplest elements, hydrogen and helium, which were forged in the first few minutes of the universe's existence, and trace the earliest production of heavier elements like carbon and oxygen, which were later cooked up in the first generations of stars. These black holes are not just monsters, they are the universe's most reliable historians, their brilliant beacons illuminating the very chapters of cosmic dawn. Our journey through these 30 facts inevitably circles back to one pressing question. Could the immense power of a supermassive black hole ever reach out and threaten our world? The answer is a profound and definitive no, a reassurance written in the fundamental laws of celestial motion. The danger from a black hole lies in its proximity, and Sagittarius, a star, is cosmically distant. We orbit the galactic center from a safe perch 27,000 light-years away, a distance so vast it renders our local Titan harmless. Our solar system is not falling inward, it is gracefully sweeping around the galaxy in a stable, 230 million-year orbit, much like Earth circles the Sun. This balance is not fragile luck, it is the enduring result of the galaxy's gravitational dynamics. The collective pull of all the stars, gas, and dark matter in the Milky Way creates this stable path, a cosmic dance floor where we have circled for billions of years. Even if Sagittarius, a star, were to suddenly awaken into a brilliant quasar, its deadly radiation and particle jets would be aimed randomly into space, not targeted at our distant corner. The sheer scale of the galaxy is our ultimate shield. The true threats to Earth are far more local, like a chance asteroid impact or the eventual death of our own sun in billions of years. The supermassive black hole at the heart of our galaxy is a distant anchor, a silent force that guides our long cosmic journey without ever reaching out to harm us. This final fact brings our exploration to a comforting close, a reminder that understanding these dark giants dissolves fear, replacing it with awe for the immense and stable cosmos we call home. The sheer scale of these cosmic giants permanently alters our sense of place. We have encountered black holes so vast their event horizons could swallow our solar system thousands of times over, and we have witnessed the subtle, elegant proof of Einstein's universe in the frantic orbit of a single star. From the sleeping Titan in our galactic core to the brilliant, ancient beacon of TUN 618, these are not mere destroyers. They are fundamental architects regulating the birth of stars, shaping the growth of galaxies, and perhaps even holding the key to the universe's deepest mysteries, from the nature of information to the fabric of spacetime itself. Their story is one of immense power and profound influence, a narrative where darkness gives birth to the brightest lights and where gravity writes the rules for cosmic structure. Each fact reveals a universe far more dynamic and interconnected than we ever dreamed. So, which of these truths reshaped your understanding the most? Was it the timeless nature of a black hole destined to outlive the stars, or the ghostly bubbles that testify to our galaxy's violent past? Share the fact that amazed you most in the comments below, and if you are ready to continue unraveling the cosmos, subscribe for more journeys into the greatest space mysteries.